Hello everybody. I welcome you all to Unit 14 of Biomolecules, Part 2. In this particular video, we are going to learn about the preparation of glucose, monosaccharides, the preparation of glucose and its structure elucidation, and also the configuration of glucose. In this particular video, this is all what we are going to discuss. So I want all the students to keep their notebooks and pen with them, and I want you to take down certain points as and when we go through the presentation. So let's get started. We will start with monosaccharides, glucose. Glucose is generally obtained or is found in nature freely in most of the fruits as well as in ripe grapes. It is also found very commonly in a combined form along with fructose in sucrose, cane sugar. Let us proceed towards the preparation of glucose. Now, how do we prepare this glucose in a laboratory or any industry? So, one of the methods of preparation is from sucrose, cane sugar. Sucrose has the formula C12H22O11. When we are going to subject it to acid hydrolysis, that is, we are going to have breaking down of the molecule of our sucrose using acidic conditions, you are having glucose and fructose obtained. This is one of the methods to prepare glucose. The second method which we are going to discuss is preparation from starch or cellulose. Starch is a polysaccharide. It has the formula C6H10O5 times. When we subject it to hydrolysis in an acidic medium and 2 to 3 atmospheric pressure and 393 Kelvin temperature, you obtain glucose. So the two methods of preparation of glucose could be either from a disaccharide, sucrose, or from a polysaccharide, starch or cellulose. Now let us understand the structure elucidation of glucose. Now, what is the meaning of structure elucidation? This is the method to identify the structural features of glucose. How are all the carbon atoms arranged? What's the functional group? How is the functional group arranged? Etc. That is what we come across under structure elucidation. Now, you must be wondering, how do we go about? So first and foremost, we must try to find out in glucose how many carbon, hydrogen, oxygen elements are present. So we proceed towards something called as the elemental and molecular mass determination. Elemental analysis and molecular mass determination, you must have come across about this in first PUC, where we all had learned the quantitative and qualitative analysis of organic compounds, which help us to identify the elements present. So from that, we have identified the elements present in glucose to be carbon, hydrogen and oxygen, and also we have identified the number of atoms of carbon is 6, hydrogen is 12, oxygen is 6, and thus we have the molecular formula of glucose as C6H12O6. This is how we obtain the formula from the elemental and molecular mass determination. Next, what is the functional group that could be present in glucose is the big question which should be appearing in all our minds. So now we proceed towards reaction with hydrogen iodide. Hydrogen iodide is a good reducing agent. So hydrogen iodide in the presence of red phosphorus acts as a reducing agent. Now the question is, what is reduction? Reduction is removal of hydrogen or addition of oxygen. Is that what is coming to your mind? No. Reduction is addition of hydrogen or removal of oxygen. This is the definition of reduction. So now when we are looking at the formula of glucose, which we have written as CHO and CHOH and CH2OH. Let us react it with hydrogen iodide and red phosphorus. When we do this, there is reduction happening at all the carbon atoms. So the definition of reduction, removal of oxygen, addition of hydrogen. So let us understand, if you look at this first aldehyde group, we are removing the oxygen and we will add hydrogen. As a result, you are having the product with N-hexane where the first carbon atom has got 3 hydrogen atoms because you have removed the oxygen and added hydrogen. Likewise, you are observing the next 4 carbon atoms, which is CHOH. You have removed the oxygen and we are adding hydrogen. So we are getting the next 4 carbon atoms, which is all reduced. You are getting the formation of CH2 groups. And the last carbon atom obtained is because of reduction, where the formula is now called N-hexane. So here you will observe N means straight chain. So if the product has got straight chain, if the product, what we are writing or written here, N-hexane as straight chain, that means the reactant glucose should also have a straight chain, indicating that as there is a straight chain of carbon atoms in the product, the glucose also must have 6 carbon atoms which are all arranged in straight chain. Thus, we have got an idea about the arrangement of carbon atoms. Now, let us try to identify the other functional group. We have a reaction with hydroxylamine. Hydroxylamine is NH2OH. Hydroxylamine is a reagent which reacts easily or undergoes condensation reaction with all carbonyl compounds. Now, what are carbonyl compounds? Carbonyl compounds are aldehydes and ketones. So now we will try the reaction with glucose. So what we do, we take glucose and allow it to react with hydroxylamine. Hydroxylamine is going to have loss of H2 here, and oxygen from the aldehyde part of glucose is also lost, resulting in the formation of a product which is having carbon nitrogen double bond, and the rest is N single bond OH. The compound is called glucose oxime. This is due to condensation reaction. That is why there is loss of water. So what does this signify? This signifies that there is a carbonyl group in glucose. So let us try another one reaction. That is the reaction with hydrogen cyanide. Hydrogen cyanide undergoes addition reactions with all carbonyl groups, that is all aldehydes and ketones. So here also it reacts with glucose. Let's check that reaction out. So if you take glucose and allow it to react with hydrogen cyanide, you are going to get a product which is called glucose cyanohydrin. What has happened? We are having the hydrogen part of hydrogen cyanide reacting or attacking the oxygen of aldehyde group and converting it into OH, and the cyanide part attacking the carbon atom of our aldehyde group to convert into the compound which is called glucose cyanohydrin. So what does this signify? This signifies the presence of, again, the carbonyl group or aldehyde or ketone. Carbonyl means aldehyde or ketone. So these two reactions, reaction with hydroxylamine as well as reaction with hydrogen cyanide, indicates the presence of carbonyl group in glucose. So it is confirmed that the 6 oxygen atoms what are present in glucose, 1 oxygen atom must be an aldehyde or ketonic group. Now the next question that comes to the mind is, what is that carbonyl group? Can it be aldehyde or is it ketone? So we will try the reaction with bromine water. Bromine water is a very mild oxidizing agent. So it is observed aldehydes readily are oxidized to give carboxylic acids, and ketones do not get oxidized easily. And if at all ketones get oxidized, they will get oxidized to give carboxylic acids with 1 carbon atom less when compared to the starting compound. So let us try the reaction with bromine water. So when we are taking glucose and reacting it with mild oxidizing agent bromine water, we are getting the product called gluconic acid. Now what is happening here? If you will carefully observe, the aldehyde group has got only oxidized to carboxylic acid group, COOH. Addition of oxygen has happened to give you COOH group, carboxylic acid group. That means there should be definitely an aldehyde in glucose, because if you will observe, the total number of carbon atoms in glucose remains to be 6. That is count. This is 1 and here there are 4 and here there is one more. That is altogether 6. And we just had discussed, if aldehyde is undergoing oxidation, it should give us a product containing same number of carbon atoms and only aldehyde will get oxidized to carboxylic acid. So glucose is getting oxidized to gluconic acid, confirming that the carbonyl group is aldehyde. Later, the test for aldehydes also confirmed this. When glucose was reacted with Tollens reagent, it gave a black precipitate with Tollens reagent, confirming the presence of aldehyde group. This is a characteristic test answered by all aldehydes. So the significance of reaction bromine water indicates that the presence of aldehyde group. So now let us try to check what is the other functional group present in glucose. So the reaction performed is with acetic anhydride. So we take glucose and allow it to react with acetic anhydride. Now acetic anhydride is having the formula CH3CO twice O. This is the formula for acetic anhydride. Acetic anhydride readily reacts with all alcoholic groups. This is the alcoholic group. 4 molecules are there here, and we have one more alcoholic group here. So what does it do? Acetic anhydride will substitute the hydrogen atom of the alcoholic group with an acyl group. And what is an acyl group? It is COCH3 group. You can observe this is the one, COCH3 group 4 times. And if you'll observe CH2OH, this hydrogen is getting substituted by an acyl group, which is CH3CO CH3 group. So when glucose was reacted with acetic anhydride, the product called glucose pentaacetate was obtained. This confirmed that glucose has 5 hydroxyl groups, OH groups, because you are getting pentaacetate product. But it also is very important to remember and note this, that a carbon atom cannot have more than one OH group, hydroxyl group. If it is there, it is unstable. It will decompose or it will break down and water is lost. In case of glucose, it's a very stable compound. What does it mean? It means that the 5 OH groups must be present on 5 different carbon atoms. So now let us look into the reaction with nitric acid. Nitric acid is a very strong oxidizing agent. Now what is the purpose of reacting with nitric acid? Nitric acid will oxidize the aldehyde group which is present in the molecule of the glucose, which is already known to us, and it will also oxidize the primary alcoholic group if it is present. So the molecule of glucose is reacted with aldehyde containing aldehyde and primary alcohol and secondary alcoholic groups. All are present in the molecule of glucose. It is subjected to oxidation using concentrated nitric acid. The product obtained because of oxidation was a dicarboxylic acid. A dicarboxylic acid is the compound where you are having acid groups at the terminal positions of the carbon chain, and the product obtained because of oxidation of glucose was saccharic acid. So the product saccharic acid confirmed that the aldehyde group which is present in glucose is undergoing oxidation to give you carboxylic acid group, and the primary alcoholic group, which should be the last carbon atom, is also getting oxidized to give carboxylic acid. Thereby, this gives confirmation that there is the presence of a primary alcoholic group in the molecule of glucose. So now we are having all these information with us with regard to the straight chain of carbon atoms in glucose, the presence of aldehyde functional group, the presence of 5 alcoholic groups, the presence of a primary functional group. With all this information available, Emil Fischer, a very eminent scientist, he gave the open chain structure of glucose. The open chain structure of glucose is as you see here on the screen. Here you have 6 carbon atoms in a straight chain which is arranged like this. You are having the first carbon atom to be an aldehyde. The second carbon atom is an alcoholic group with H on the left and OH on the right. The third carbon atom has got OH on the left and H on the right. The fourth carbon atom has got H on the left and OH on the right. And the fifth carbon atom has got H on the left, OH on the right. And the sixth carbon atom is a primary alcoholic group. So this was the open chain structure of glucose proposed by scientist Emil Fischer. In honor of Emil Fischer, the structure is also called as the Fischer structure of glucose. Let us now understand the open chain structure of glucose. In the open chain structure of glucose, glucose is named as D plus glucose. So now when it is named as D plus glucose, what is this D? What is this plus? You must be wondering, right children? So now let us understand what is the explanation given to understand D and the term plus. D always refers to the configuration of the molecule. So, it is written before the name to explain, to represent the configuration, and plus represents the dextro-rotatory nature of the molecule. Now you will be wondering, what is dextro-rotatory and how is this term coming about? And what is this plus sign indicating? So now, to understand this better, we will take the help of a polarimeter. The schematic diagram of a polarimeter is before all of us. Now, before we go to understand the polarimeter, I would like to throw some light on what is the aspect that we are discussing about now. It was observed that the compounds which are optically active, they are able to rotate the plane of polarized light. This is what an optically active compound can do. So, what is the meaning of that? Let us understand it briefly. If you are talking about light coming out from a source, the light has light radiations which is vibrating in all different planes. This light is called non-polarized light or unpolarized light. When this light is passed through a polarizer, that time the light radiation in only one plane is allowed to emerge. This is that polarized light. So the light radiation traveling in only one plane which emerges out is called polarized light. When this polarized light is passed through a sample tube in which you are having glucose, which is optically active compound, the molecule of glucose can rotate the plane of that polarized light. You could see this is the first ability of the molecule of glucose to rotate. Slightly more rotation is seen when compared to this plane. Then you go towards this There's more rotation of the plane polarized light. So, if the molecule rotates the plane polarized light in the right-handed direction or clockwise direction, then the compound is called dextrorotatory compound. The term dexter in Latin means the right side. It's a dextrorotatory compound, which is indicated with a plus sign written within parenthesis. If the compound could rotate the plane of polarized light in the anti-clockwise direction, the left-handed direction, then it is called levorotatory compound. Now, glucose is always called plus glucose because it always rotates the plane polarized light in the clockwise direction, and glucose is said to be an optically active compound. Hence, it rotates plane polarized light in the clockwise direction, which is written as plus sign within parenthesis. Now, how do you explain and understand the terms D or L? The term or the letter D or L written before the name of any compound will always indicate the relative configuration when the compound structure is compared with the reference compound called glyceraldehyde. So, one thing must become clear, students. D does not refer to dextrorotatory. Never. Please don't get confused with this. D, it refers to the configuration when compared to the structure of glyceraldehyde. This is what you are supposed to keep this in mind. So let us understand this. This is the compound of glyceraldehyde. The molecule of glyceraldehyde is supposed to be optically active. Now why? I want you to observe the carbon atom which I have indicated is bonded to 4 different groups. You can see this and all these groups are different. Hence, when it is placed in front of a mirror, such a carbon atom will get an image which is inverted. The mirror image is inverted, as you also have seen yourself in the mirror. Your right hand would look like the left hand. The left hand would look like the right hand. So, this carbon atom which is attached to 4 different atoms or groups is called chiral carbon atom, and it is having a non-superimposable mirror image. Let's look at the example of glyceraldehyde. If you look at glyceraldehyde, you are having the first carbon atom is the aldehyde, the second carbon atom has got H on the left, OH on the right, and the third carbon atom is CH2OH. Whenever the OH group on the carbon atom which is asymmetric, the second carbon atom in this case of glyceraldehyde, the first carbon atom is aldehyde, the second carbon atom is asymmetric or chiral. Why is it chiral? I want you to understand again. Are you observing? It is this carbon atom is bonded to 4 different groups. Which are they? Aldehyde, the other one is hydrogen, the other one is CH2OH, the other one is alcohol. So the carbon atom, the second carbon atom is chiral. Whenever the chiral carbon atom has OH on the right side, it is called D plus glyceraldehyde. If the OH group is on the left side, then it is called L plus glyceraldehyde. I want to repeat. D means OH is on the right side of the chiral carbon atom. L means OH is on the left side of the chiral carbon atom. Plus sign indicates dextrorotatory, rotating the plane polarized light in the clockwise direction. That is called as plus sign dextrorotatory. Now always the mirror image will be the opposite rotation it will have. So if you will observe, L-glyceraldehyde is the mirror image of D-glyceraldehyde. So therefore, L-glyceraldehyde is having optical rotation in the anti-clockwise direction. Minus sign is indicated within parenthesis. It is called levorotatory. Again I repeat, D means the configuration. Plus sign indicates the rotation of the plane polarized light. So glyceraldehyde was taken as a reference by Emil Fischer. So we are by convention continuing to use that as the reference compound. So if you will observe the highlighted part which is seen here, in the case of glyceraldehyde, the carbon which is chiral, the second carbon atom has OH on the right side. Just like that, please look at the molecule of glucose. The carbon number 1 is aldehyde, 2 is having HNOH, 3 is having OHH, 4 is having HNOH, 5 or the fifth carbon atom has got H to the left, OH to the right. The fifth carbon atom is supposed to be called as the lowest asymmetric carbon atom, the lowest chiral carbon atom, because you start numbering always from the aldehyde. So carbon 5 is the lowest chiral carbon atom. If it is having OH to the right, it is very similar to how it is arranged in the case of D-glyceraldehyde. Hence, glucose is also named as D-glucose with reference to glyceraldehyde, D-glyceraldehyde. Plus sign indicates that the molecule of glucose rotates the plane polarized light in the clockwise direction. So let us again remember, D is the arrangement of the OH group on the fifth carbon atom on the right side, very similar to what is seen in glyceraldehyde, D-glyceraldehyde. So the name is given as D, configuration is called D. Plus indicates the molecule of glucose rotates the plane polarized light in the clockwise direction. That is, it is dextrorotatory. Now let us understand something about the cyclic structure of glucose. It was observed that the open chain structure of glucose could not answer many of the points what was observed whenever glucose was subjected to chemical reactions. It was noticed that glucose does not answer Skiff's test. Now what is the Skiff's test? All aldehydes will immediately give pink color with Skiff's reagent. So if you will add a Skiff's reagent to an aldehyde group, immediately you should get pink color. Glucose has aldehyde group, that's what we have discussed. But when you add Skiff's reagent to it, you do not get that pink color. So this was very baffling, very confusing. Glucose has aldehyde, we have discussed, but it is not answering this chemical test with Skiff's reagent test. There was one more test done, that was the pentaacetate group of glucose could not react with or did not react with hydroxylamine. So this indicated that there was no free aldehyde group. And very important, glucose existed in two crystalline forms, one called as alpha, the other called as beta. So all these discrepancies, these behavior could not be explained by the open chain structure of glucose. That is why the ring structure or the cyclic structure of glucose was presented. Now let us look at the structure of glucose open chain. I want you to look at the center molecule, what we can see on the screen here. The first carbon atom is aldehyde, carbon number 1, it's all numbered. Carbon number 2 has got H on the left, OH on the right. Carbon 3 has got OH on the left, H on the right. Carbon 4 has got H on the left, OH on the right. Carbon 5 has got H on the left, OH on the right. And carbon 6 is CH2OH. Now students, whenever you observe or you take the compound of glucose, it is found just about there is 1% chance that the molecule could exist in this open chain structure. 99% chance the molecule of glucose would get converted into a cyclic ring structure, what is seen on the left and on the right side. So what should be the reaction happening? The aldehyde group CH double bond O, the oxygen of the aldehyde will take the hydrogen atom of the OH group on the fifth carbon atom. As a result, the aldehyde group will no longer remain as aldehyde, but that CH double bond O aldehyde will get converted into an alcohol. It will get converted to C single bond OH group. At the same time, the oxygen on the OH group of fifth carbon atom will attack the carbon 1 of the aldehyde group. So what do you see because of that? I want students to concentrate on alpha D plus glucose structure. Let's compare this structure with the open chain structure next to it. Let's observe. Carbon number 1 has got H on the left and OH on the right. Carbon number 2 has got H on the left and OH on the right, very similar to the open chain. Carbon number 3, OH on the left and H on the right, similar to the open chain structure. Carbon 4, H on the left and OH on the right, very similar to structure or carbon 4 in the open chain structure. Carbon 5, H on the left, but is involved in the formation of a ring with our carbon number 1. This is how it is happening. And carbon number 6, it is very similar to what is seen in the open chain structure CH2OH. Now this is called the ring structure or cyclic ring structure of glucose. Let us concentrate on carbon number 1. Carbon number 1 is called the anomeric carbon. Why? Because it is the carbon 1 which was previously the functional group aldehyde, and it is only that carbon from where the ring structure has started. So it is called the anomeric carbon. Whenever the anomeric carbon has OH group on the right side, then it is called alpha. If the OH group on the primary or the anomeric carbon is on the right side, the compound should be called alpha, and of course the configuration is D and plus is the rotation shown, hence the name is alpha D plus glucose. Come to the beta. If you are having on carbon number 1 the anomeric carbon, the OH on the left side, then you call the compound and the structure as beta D plus glucose. The meaning of D is a configuration with reference to glyceraldehyde plus the molecule rotates plain polarized light in a clockwise direction. So alpha D glucose beta-D-glucose can only be seen for the cyclic structure of glucose. Let us now understand in a more simpler manner the Havard structure of alpha and beta D glucose. Now children, mind you, the Havard structure given by scientist Havard is only seen for the cyclic structure of glucose. That is the alpha and the beta form. It is not seen for open chain structure of glucose. Now, scientists Havard took the reference of a pyran heterocyclic ring. Pyran has got, if you can observe, there are how many carbon atoms? Let us count 1, 2, 3, 4, 5 carbon atoms and an oxygen in the ring. So he took the help of a pyran ring to write the structure in the form of Havard structures. Let's check the structures now. I want students to see the Havard structure, which we write it as alpha D plus glucopyranose. You are going to always write the Havard structure after understanding the Fischer structure, which is written as a reference and comparison for you to understand on the left side. So, you are having always in the Havard structure the oxygen atom written at the top right hand corner and the regular pyran ring is drawn. You will start numbering from here, from the carbon atom below oxygen to the right as 1, 2, 3, 4, 5. Now the rule to write the Havard structure. When you look at the carbon skeleton in our open chain structure, from C1 to C6, whatever is on the left side of the carbon skeleton should be written above the plane in the Havard structure. Whatever is on the right side of the carbon skeleton should go below the plane in the Havard structure. This is the rule. So let us try to understand. We have drawn the Havard structure ring. So carbon 1, I want the student to keep comparing with the Fischer structure which is on the left side. So I go focus on the Havard structure, the ring structure with the pyranose ring reference. So carbon number 1, H above the plane, OH below the plane, because in the Fischer structure on carbon 1, H is on the left side, so above the plane, OH is on the right side, below the plane. Carbon number 2, H on the left side, so above the plane, OH on the right side, below the plane. Carbon number 3, H on the left side, so above the plane, OH on the left side, so above the plane, and H on the right side below the plane. Carbon number 4, H above the plane because H is on the left side, OH below the plane, OH is on the right side. Coming to carbon 5, it has got a hydrogen and a CH2OH group attached to it. If you will observe, hydrogen and CH2OH. The bulky group CH2OH is placed above the plane here, sixth carbon atom, and H is placed below the plane. So thus we get the structure of alpha D plus glucopyranose. So one easy way to remember the structure, I want everybody to always practice it like this. First draw the pyranose ring. So draw oxygen at the top right hand corner and draw the hexagon. Then start showing bonds at every carbon atom. Now start numbering from the carbon atom below oxygen to your right and go clockwise the numbering 1, 2, 3, 4, 5. and always have to put on carbon number 1 OH below the plane, carbon 2 OH below the plane, carbon 3 OH above the plane, carbon 4 OH below the plane. Let's keep this in mind, and from that we can write the others. I repeat, what is there? OH on carbon 1 below the plane, OH on carbon 2 below the plane, OH on carbon 3 above the plane, OH on carbon 4 below the plane. So how to remember this? I would remember it like this. When I was a student, you could write out carbon 1, I go about in order down, down, up, down. So you have OH down, OH down, OH on third carbon up, OH on fourth carbon down. So if you put OH first, the remaining positions are filled with hydrogens. Except on the fifth carbon atom, CH2OH goes above the plane. So, what's the pattern for writing alpha D glucose? Down, down, up, down. Let us now understand the structure for beta D plus glucose, which is written as beta D plus glucopyranose. Now, children, we are comparing it with the open chain beta D plus glucose, which is on the left side of the structure or the screen. So you are having carbon number 1 having OH above the plane, H below the plane as per the open chain structure of beta D plus glucose. Carbon number 2, you have H above, OH below. Please keep observing the open chain Fischer structure which is on the left. Carbon 3, OH above, H below. Carbon 4, what is there? H left side, OH on the right side. But here what is it? H on the left, OH on the right. Carbon 5, what do we have? CH2OH bulky group above the plane and H below the plane. So this is the structure for beta D plus glucose. So students, you should know that the Havard structure is what is asked in the examination. So do practice the Havard structure. I again give you the clue or the tip to write the beta D plus glucose or glucopyranose structure in the Havard form. This is the method. Draw the hexagon with oxygen at the top right hand corner and show bonds at every carbon atom. Once you have shown bonds at every carbon atom, the pattern for beta is up, down, up, down. What was the alpha, children? It was down, down, up, down. Now how do you have for beta? The beta will be up, down, up, down. So this is how you are able to understand the configuration of the glucose molecule alpha D plus glucose in reference to pyranose ring. So it is called alpha D plus glucopyranose. The other one beta D plus glucopyranose. These are the Havard structures of glucose. Now, what is this term anomers? Anomers are a pair of optically active isomers which will only differ in the arrangement of the groups, that is called configuration, around carbon number 1. I want students to look at the example alpha D plus gluco or glucose, and the other one is beta D plus glucose. Please observe carbon number 1 on the alpha D plus glucose. OH is on the right. Please observe carbon number 1 on the structure of beta D plus glucose. OH is on the left. So it is clear that these two structures, alpha D plus glucose, beta D plus glucose, they are called anomers. The next terminology which we have to learn is called epimers. Here, epimers are nothing but a pair of optical isomers which differ in the configuration around any carbon but not carbon number 1. Let's take the example. The example is glucose and galactose. I want students to observe the formula for glucose. It is carbon number 1 HOH, carbon number 2 HOH, carbon 3 OHH, carbon 4 H on the left, OH on the right, carbon 5, carbon number 6 CH2OH. The compound is called alpha D plus glucose. Now we are going to observe the formula for the alpha D plus galactose. This is an epimer of glucose because it differs in the configuration at 4. Can you check that out? The fourth carbon atom in glucose has got H to the left, OH to the right. In case of galactose, OH is to the left, H is to the right. So this is what you are observing in the case of our alpha D plus galactose. It differs at configuration of carbon number 4 with glucose. So alpha D plus glucose, alpha D plus galactose, they are epimers of each other.